our pleasure to have Sebastian from Princeton University visiting us. Sebastian is the OR department.
Yes.
It's an OR in Princeton. And new there, but he's already received all sorts of awards, paper award, other impressive honors that you can read up on his website. And also, I think he's going to start what I hope is a nice tradition of whiteboard presentations.
Thank you very much for the introduction. Okay, so I'm going to tell you about random graphs and clique numbers and perhaps a new proof technique which is based on minimax hypothesis testing. I will try to explain everything. So first, why do I want to look at random graphs and cliques and things like that? So I don't think I need to convince you that networks are basically everywhere. And the data that we get is increasingly more common that data is actually a network. And so as statisticians or probabilists or even engineers, it's quite common to make the assumption that the network was randomly generated. And then, based on this assumption, we want to leverage this assumption and use the properties of these random networks to do something else. Okay, maybe you have agents interacting with the network, or I don't know. You can have many, many things. So what you want to do is to understand the properties of the network. So let's see what kind of models for random network have been out there. So the most famous model is the Erdős-Rényi model. Erdős-Rényi. So in the Erdős-Rényi model, we have a graph, G. So G is just a set of vertices and a set of edges. So V is a finite set, and E is a set of pairs of elements in V. And when I say that G is a random graph, what I mean is that E is going to be a random variable. Okay? So in the Erdős-Rényi model, I'm going to call this Gn. So that's the Erdős-Rényi on n nodes. And it's going to depend on some probability P. So that's the GNP. And the set of vertices in that case is simply the set of elements from 1 to n. Okay. And this set of edges, En, is a random variable. So what does this random variable satisfy? It satisfies the following. So it satisfies that for any I not equal to j, the probability that ij, so that there is an edge between I and j, meaning that ij is an element of En, this probability is p. So what does it mean? It means that if I take two nodes, the probability that they are connected is p. That's the first property of an Erdős-Rényi. The second property is that these events are independent. So these events are independent. And that defines the probability distributions over graphs on n nodes, these two properties. And now, so this model has been out there for 60 years. It has been very, very useful in many, many different contexts. And we know basically everything that there is to know about this model. There has been various extensions, such as stochastic block models, which goes a little bit further by assuming that you have different communities, and different communities have different values for P, but you still always assume that two edges, the fact that two edges are present, are two independent events. Okay. Now, in real-life networks, this assumption B is definitely not reasonable. Okay? It doesn't make sense if you have A, B, and C. Think of a social network. If I know that A is friend with B and A is friend with C, then it's probably more likely that B and C are going to be friends. Okay, so what this means is that you don't have this type of nice independence in real-life networks. Okay, so an edge, whether or not an edge is present, depends on the other edges. And this is not captured by the Erdős-Rényi, and it's not captured by the stochastic block models. So what other kind of random graph do we have? one of them, which has been studied for also maybe 30 years, something like that, is a class of random geometric graph. So what is a random geometric graph? By the way, you can interrupt me at any time if you have a question or if something like that. So what is a random geometric graph? So you start with a metric space, x delta. So x is a space and delta is a metric. And you have a probability distribution over this metric space. So you take x1 up to xn, IID from some measure, from some probability measure on x. And then what you do is that you are going to build a graph again on n vertices where I and j are going to be connected if xi is close to xj. Okay. And now connect I and j if, let's say, the distance between xi and xj is smaller than some value, let's call it r. But now you see, thanks to the triangle inequality, you have dependencies between the edges, right? If I know that A is connected to B and A is connected to C, it means that B and C are in a ball of radius R around me. Okay, so conditionally on this, I know that B and C are at most distance 2R. So it becomes more likely that there are distance R when I condition on this edge. So now we start to see dependencies between the edges, and we like that. So think again of social networks. What would it mean? It means that everyone in the social network has a feature vector associated to him, and we decide whether or not to be friends based on these feature vectors. If they are close enough, then we become friends. Okay, so perhaps this is, at least this is a step in the direction of a model which would be more realistic for real graphs. Okay. So we want to study this model, but now let's look at one specific example of this model because it's very general, right? We are in a metric space, we have a general measure. I'm going to look at the specific case where the metric space is just the Euclidean sphere. Because in that case, and the metric is just the Euclidean metric, in that case, when you're on the sphere, it only depends on the inner products, right? So we get linearity, and we like linearity because it makes everything easier. So let's consider the case where x is just a sphere in dimension d minus 1. Okay, so that's a set of points x in RD. So that's the norm of x is 1. And again, delta is the Euclidean metric, and I'm going to take the measure to be the uniform measure on the sphere. Okay, so now what I will call a random geometric graph, and I will define this as G and D of the dimension, and it's also going to depend on P, is as follows. So I take x1 up to xn, IID uniform on the sphere, and I connect them if they are close enough. So ij is going to be in my set E and D, right? So this random geometric graph is now on n vertices, and the set of edges is E and D. So an edge is going to be in E and D if and only if. So the norm of xi minus xj is smaller than something, let's call it R, which is going to depend on P and D. So as I said, because the norm of xi and xj is 1, this is equivalent to saying that I just want to check if the inner product is larger than something, let's call it T, TPD. And now I want this threshold to depend on P in the sense that I want the probability of this element to be P. Okay, so where TPD is such that the probability that, let's say, the inner product between x1 and x2, when x1 and x2 are uniform on the sphere, that this is larger than TPD is equal to P. Okay, there is a number which says so. So now this random geometric graph, it satisfies property A. Okay, so it's homogeneous. The probability of observing a given edge is P, but you don't have independence anymore. And now, basically, what I would like to do is to do what we did for the Erdős-Rényi, but in this new model, in this more realistic model. So as I said already, I'm not the first one to ask this type of question. This has been studied for at least 30 years. But now the new twist is that this has been studied in the case where the dimension d is fixed, and you look at the number of points that grows to infinity. You look at you throw more and more points on the sphere, and you look at the properties of the network that you get. But now in nowadays application, if you think of high dimensional blah blah blah, you want d to depend on n. Okay? You want to have d that grows as the number of elements or elements in your data or whatever. So we want to understand what happens when d depends on the dimension. And we will see completely new phenomenon. Yes?
What does the dimension tell you about the network included?
Right, so intuitively think again of the social network. The dimension is the number of real numbers that are going to tell if we become friends or not. Right? It's the dimension of the feature vector.
Okay.
It's how many information I can put in this vector. Right? So as d grows, you expect the network to become more complicated in some sense. Right? You have more flexibility in some sense. No, not necessarily. No. I mean, of course, we'll see what happens when d is large. Okay, so we are going to ask this question for a very specific parameter, which is the clique number. Okay, so what is the clique number? So the clique number, omega of g, of a graph in general, it's the size of the maximal clique. Okay, so it's the max of cardinality of S over all subset S of 1 to n. Or let's say, in general, S is a subset of B, such that for any I not equal to J, I and J in S, the edge Ij is in E. Okay, so that's a clique number. I look at a clique. S is a clique if it's a set of vertices such that for any two vertex in my set, the corresponding edge is also present. And now I look at the maximal clique, and this is called the clique number. And I want to study the clique number for random geometric graph when d depends on n. That's what I'm going to do now. So let's look at first what happens for the Erdős-Rényi. Okay, so one of the first things that Erdős-Rényi proved is that if you look at the clique number, also to make things simpler, but you can generalize, I'm going to focus on the case where p is 1/2. Okay, so from now on there won't be any p. The probability of having an edge is going to be 1/2. Okay, so in the Erdős-Rényi it means I flip a coin for every edge. In the random geometry graph it means that TPD is 0. Okay, so I take two vectors uniformly on the sphere and I connect them if their scalar product is positive. That's my random geometry. So the first theorem is a result from Erdős-Rényi is that the clique number of an Erdős-Rényi with p equals 1/2, if you rescale it by 2 log n, so log in base is 2, that tends almost surely to 1 as n goes to infinity. Okay, so in an Erdős-Rényi, right, it's a random object, but in the limit we know exactly what is going to be the clique number. It's 2 log 2n. Actually, yeah. So this means that this is equivalent to this, and we know it up to second order. Okay, we actually even know that this thing is concentrated on only 2 values. Okay, it's quite amazing, but not when you rescale it. Just like that. Okay, so that's the theorem for the Erdős-Rényi. Now let's try to get some intuition for the random geometry graph. So let's look at what happens when d is fixed. Okay, so I'm going to think of d being fixed, and maybe n goes to infinity. So the picture looks like this, right? So that's Rd. And what I'm drawing here is just the positive orthants. That's R plus d. Right? How many orthants do you have? You have 2 to the d orthants in Rd, right? I can flip a sign and I get 2 to the d orthants. Now, if you look at all the points that fall in an orthant, they will be connected. Right? Because they all have the same sign. So when I take the inner product, it will be positive. Right? I have my sphere here. drawing, but you have the sphere. So any set of points which is contained in an orthant like this, they will be connected. There are 2 to the d orthants, n points, so at least one of the orthants contain n over 2 to the d points. Okay, so clearly omega of G and D is larger than n over 2 to the d. And that's just true, right? That's true for D1 and for any n and for any d. So you see, think of d being fixed. 1 over 2 to the d is just a constant. So here the clique number is linear in n. Okay? It means that you have huge cliques. So in a social network, if people decide on whether or not they are friends based on just a few parameters, you will get huge cliques. Okay? Which sort of is meaningful. But you see, it's completely different from the Erdős-Rényi, right? In the Erdős-Rényi, you get only very small cliques. Okay. And you see, you can push that up to d being little o of log n. When d is little o of log n, okay, maybe it's not linear in n, but at least it's certainly polynomial in n. Okay, so up to d, so d equals little o of log n. You have that and d is super polynomial. Okay, so this thing is omega of n to the 1 minus epsilon for any positive epsilon. Okay, so before log n, when the dimension, the number of features is less than log n, log the size of the network, you have more than polynomial sized cliques. So that's one extreme, when d is small. Now let's look at the other extreme when d goes to infinity. So when d goes to infinity, what happens? So now we think of n being fixed, and the dimension grows. So does anyone have a guess of what happens when d goes to infinity? So, right, the sphere becomes infinitely dimensional. So basically the coordinates that are going to decide for any 2 points whether or not they are connected, let's say for x1 and x2, they will have nothing to do with the coordinates that will decide for x1 and x3 being connected. Right? There is absolutely no reason why there would be overlap between the coordinates that decide if x1 and x2 are connected and the coordinates that decide for x1 and x3 being connected. Because n is finite and d goes to infinity. So what this means is that you will get independence. Okay? You will get independence, so you will get back the Erdős-Rényi model. So what you can show is that actually in terms of distribution, G and D tends in total variation as D goes to infinity to an Erdős-Rényi. Okay, so, and this was proved by DeVroy, Georgi, Rigosi, and Ludina in 2011. But let me, so I will discuss other results of this paper, so I can say this. This is absolutely not deep, right? I mean, the proof is one line, so maybe we can do it. So let's see. So how do you decide if two vertices are connected? So xi, I'm going to write it as xi1, etc. up to xid. So whether or not I and j are connected, I look at the inner product. So I look at the sum for t equals 1 to d of xit xjt. Right? And I look at, is this positive? That will tell me if I is connected to j. So now let's rescale this. And let's look at this as a vector of pairs, ij. Okay, so ij included in. So for any pair, so this is a vector in dimension n choose 2. Right, I have n choose 2 possibilities. And this vector, let's look at what it satisfies. So what is the expectation of this? So the expectation, let's look at every element. The The expectation of this is equal to 0. Right? The expectation of, let's call this yijt. Okay, so the expectation of yijt is 0. The variance of yijt is 1. Right? This is 1 if I is not equal to j. And what are the covariances between yijt and, let's say, yklt? So the covariance is 0 if ij is not equal to kl. Right? If I don't take exactly the same two indices, then the covariance of these two things is 0, and it's 1 otherwise. So I can just apply the central limit theorem. Right? I have a bunch of random levels which have 0 correlation, expectation 0, variance 1. So by the multivariate central limit theorem, this tends to a bunch of Gaussian random variables, right? N0, 1. So a bunch of N01 in dimension n choose 2, and each one of them being independent. Right? So now I just have N01, and I decide to connect if the N01 is positive or not. Okay, so that's it. That's a proof of this convergence. So in particular, in terms of the clique number, it tells us that when d goes to infinity, the size of the largest clique is going to be roughly of order 2 log n. Okay, by this other theorem. So now we are starting to see a picture. Picture looks like this. So there's a dimension here. Here you have the size of the clique in a GND. So what we said is that up to, so when d is finite, we have something like omega of n. Right? We have something linear when it's finite. When it's little o of log n, we have something which is maybe not quite linear, but certainly super polynomial. So it's omega of n to the 1 minus epsilon for any positive epsilon. Okay, so it goes like this. So we know up to here, and then we know that at infinity it must be 2 log 2n. At the end it must go here. And actually, so you have the central limit theorem, so you can look up for the Berry-Essen estimate. The Berry-Essen estimate will give you a rate of convergence for this. But the rate of convergence will be that this convergence kicks in when d is basically polynomial in n. So when d is poly n, by just redoing this argument with Berry-Essen, we know that we are already at 2 log n. So there is a huge gap right now between log n and poly n. So what these guys did, so first they did, how do you prove this theorem, the one upstairs with the Erdős-Rényi? You compute the first moment and the second moment for the total number of cliques of a given size. And then you just apply standard tools from the probabilistic method, and that gives you this kind of result. So you can redo exactly this argument in the random geometrical model. The calculations are more difficult, but what you get, so by just doing first and second moment method, what they proved is that, so the calculations are much more complicated, but that's the spirit. What they showed is that when d is omega of log cube n, you are already at 2 log n. Omega of GND is already smaller than 2 log 2n with high probability. And with high probability means that with probability tending to 1 as n goes to infinity. So you don't need to go up to poly n, you actually only need to go up to log cube n for this thing to be true. But log cube n, you are already almost like an Erdős-Rényi for this parameter, okay? Right? The convergence in total variation tells us much more, right? Tells us that every every parameter that you can compute on the GND is going to be the same as computed on the GN if D is polynomial in N. Here we are just saying, if you look at the clique number, then this is already true at D being log cube N. Okay. So there is still a gap between log N and log cube N. So the next thing they did goes as follows. So how can you get a clique? Well, basically what you can do is that you can just look at orthons, and you can try to rotate your orthons and try to find the best fit. Okay. So that will certainly give you an upper bound. Right. So what they did is that they said, okay, omega of GND is smaller than the sup, let's say, of a cones of the number of points in the cone. And now you just use standard tools from empirical processes and the VC dimension of the cones on the sphere. And that gives you that already at log squared n, you're not quite at 2 log n, but you are already smaller than log cube n. So what they showed is that at D being omega of log squared n, so by doing this argument, you can show that at D being omega of log squared n, omega of GND is already smaller than, it's a big O of log cube n. Okay, so already here, log squared n, you are at log cube n. Log cube n. Okay, and that's the end of this paper. And so it raises the question, like here you are polylogarithmic, and here you are super polynomial. Okay, so something is going on between log n and log squared n. So what is the picture here? So that was the question. So I'm going to show you that there is a sharp phase transition, but basically you drop from polynomial to polylogarithmic at a certain value of D. So which D do you think it is? Log n, log squared n, log to the 3 half? Do you have any guess?
Log n.
Right. So, what
star?
which one? Log star? Oh no, okay, yes. It could have been that. So, basically everybody says log n. The only guy who said log squared n was Avi Victorson. I don't know if you know him. He's quite good. And I have no idea why he said that, but it's true. Okay, so phase transition is at log squared n. Okay. So I tried to ask him why he said that, and I didn't really understand the answer. But apparently he understands what's going on. So I'm going to show you now the theorem and the proof. And yes, sure. Yeah.
First one here, where you are computing the covariance. So you
Yes.
are fixing I and J.
Yes.
So I think you should take the covariance for different T, K, and so if your I and J is fixed, and you are taking the sum over different T.
Right. So what I should do, you're absolutely correct. What I should do is look at the covariance of these big guys, right? Of 2 coordinates.
So to elements in this one.
No. Not. Oh yeah. Yes. I need to do both. I need to do both, right? I need to do within the sum and within the coordinates. So yes, I didn't do it, but it's true also.
The other one, here you chose P equal half. So
Yes.
PD is independent of D. It's always zero.
Absolutely.
But
That
if
makes
you
things
choose
much simpler.
Other P,
Yes.
such as this one also depends on D, then everything holds, or
Everything holds, but it becomes more complicated because then you have non-trivial formulas, right? You need to compute, so you need to look at spherical caps and what is the measure of a spherical cap in terms of the height. And the height is, in TPD is going to be the height at which the spherical cap is.
but I think so here you have some summation and D is going to infinity, and we're comparing that. to
Oh
zero.
yeah, yes, it
Then
still
you should
works.
compare it to something which also depends on D, and D is the infinity.
No, absolutely. So it still works. But it's not as easy. That's a good point. Any other question? So yeah, so what I was going to say is that to me the most interesting part of the talk is actually the proof of this theorem, because it relies. I mean, it's a non-standard proof, and it relies on statistics. Okay, so for once we use statistics to prove a result in probability theory. Right? Otherwise, it's like most of the time it's the other way around, but this time we will use statistics. So the theorem that we proved with Eric Castro, myself, and Gabor. It says the following. It says that with probability at least 1/2, the clique number of an omega G and D is at least some constant times exponential, some other constant, log squared n divided by d. So if let's pass this down. So if d is log 2 to the minus epsilon n, right? So if we are just before the log squared n, then this is exponential of log to the epsilon n. So what is exponential log epsilon n? So that's not polynomial, right? To be polynomial, you would need epsilon to be 1, but that's certainly not polylogarithmic, because to be polylogarithmic, something which is polylogarithmic, it's exponential, a constant, times log n. So here you don't have log n, you don't have log n, you have log to the epsilon n. So you are in between polynomial and logarithmic, you are super polylogarithmic. So what this means is that omega g and d is omega of log to the a of n for any a. Okay, so you grow faster than anything which is polynomial in log n. So you are not quite polynomial, but you are certainly much bigger than anything which is polylogarithmic. So it goes like this, and here you have a sharp. You have a sharp transition from super polylogarithmic to polylogarithmic. Okay, so now yes.
Do you know anything about the tightness before the phase transition? Do you have one?
No, so we don't know. We don't really know exactly what is going on here. So it's moving from polynomial to maybe something less than polynomial, but we don't know what's going on exactly. We don't have precise bounds.
The log cube is also a lower bound.
Log cube is an upper bound.
An upper bound is also a lower bound?
No, we don't know. It could be that it already gets at 2 log n. It doesn't feel true, but we don't know. Yeah, I should make this more precise. When what is interesting is an upper bound, it's an upper bound, and when what is interesting is a lower bound, this picture is a lower bound. But if we wanted the precise picture, we are missing some results. Okay. All right. So let's do the proof. So the proof is going to go as follows. I'm going to set up a statistical hypothesis testing problem. So I will have a null and an alternative, which will have nothing to do with this problem. But a good test for this statistical problem will be to build something that looks like a random geometric graph, compute the clique number. If the clique number is large, then I will reject, and if it's small, I stay with the null. Okay, so I will build a statistical hypothesis testing problem where my object of interest appears as a good statistic. And then I will do the following. I will prove an upper bound for this test. I will prove a minimax lower bound. And then I will say that if this was not true, my test would be better than minimax. Hence, this must be true. Okay, that will be the result. So we have to see it in action to really understand what's going on. So there will be 4 steps. Step 1 is to show you what is a statistical hypothesis testing problem. Step 2 is to explain what test I'm going to look at. So it's going to be this test that depends on the clique number. And to analyze the test. Step 3 will be to compute a minimax lower bound, and step 4 will be the conclusion saying that if this was not true, then I will get a contradiction. So let's look at step 1. So my observation is going to be a big matrix of size n by d. And under the null, so my observation is n by d. Under the null, I have only, all the entries are n01. Okay, so let's say here I have an n0 identity in n. Second row n0 identity n, etc. And every row is independent. That's my null. Okay, so I have n01s everywhere, and they are all independent.
It's ID.
Sorry?
Zero ID.
Yes, identity in dimension n.
And D.
Yeah, D, sorry. Yes, thanks. ID. Absolutely. And my alternative is going to be that there is a subset of rows which are correlated. Okay, so there exists, my alternative is that there exists S, subset of rows, let's say of cardinality K, such that coordinate by coordinate they have a covariance of rows. Okay, so I have the same thing, except now that I have these elements in S. So this is an element in S, this one is an element in S, etc. So here I have, in general, on T, X, I, T. Okay, so I is an index, J is an index, T is something between 1 and D. So I have XIT and XJT. So each row is still an N0 identity, but now I will have some correlation between these rows, and more precisely here the covariance between XIT and XJT is going to be rho, some value. So I have a subset of rows where every coordinate is correlated. So that's my alternative. Now let's see, so that's my statistical hypothesis. So let's see how to connect this with random geometric graph and what is going to be the test of interest. So here, K and rho are going to be parameters of my problem, and I will be able to play with them. Okay, I can select them as I want for the purpose of what I want to do at this. So the second step is going to be to look at the following test. So let's view each row as an element. I mean, it's a vector in dimension D. Okay, so I have a point in RD. So here I have points in RD which are scattered uniformly according to the Gaussian measure in RD. Okay. Here my points are, so most of them they are scattered uniformly, except that those guys, the K guys which are contaminated, they tend to cluster together. Right? Their coordinates have some covariance, non-trivial covariance, rho, which is positive, sorry. So they will tend to cluster together. So here, what I'm going to do is that I will build the graph. So I have my matrix, which corresponds to x1, etc., up to xn. What I do is that I build the graph G, where I is connected to J if the inner product between xi and xj is positive. So under the null, this is exactly a random geometric graph, right? Because, okay, so it's not uniform on the sphere, but I could renormalize, right? A Gaussian vector renormalized by its norm is uniform on the sphere. And here renormalizing is not going to change whether or not this is positive. So this is exactly under the null, under H0. G behaves exactly as a GND. But now under the alternative, it behaves mostly like as a GND, except for the k coordinates which are going to cluster together. Okay, so under H1, if rho is large enough, imagine rho is 1. Right? So k rows are exactly the same. So their inner product is clearly positive. Okay? And I have a cluster of size k, I have a clique of size k. So under H1, if rho is large enough, we expect a clique of size k. We expect omega of g to be at least k. And under H0, we know that since g follows a GND, we know that omega of g is going to follow omega of GND, right, which is our parameter of interest. So now I can take k as I want. I'm going to take k as the median of GND. Okay, so let's take k to be the median of GND. And we reject, our test reject, if the clique number of the graph that we built is larger than k. And we reject, meaning that we conclude to the alternative, if omega of g is larger than k. Okay, so that was intuition, these two things, and that's what we do. Yes, thank you. So under the null, we control the probability of mistake. Right? Under the null, because k is the median of omega GND, omega of j with probability 1/2 is going to be smaller than k. Okay? So the probability under the null that we reject is smaller than 1/2 by assumption, by construction. Okay, the probability that we make a mistake under the null is smaller than 1/2 by construction. This means that we did nothing under the null. I could just flip a coin with probability 1/2, I say H0, with probability 1/2, I say H1. It wouldn't do any better. So now I need to show that I have something non-trivial under the null, under the alternative. Okay. No, this is true for any A. Right? I mean, if it's true for A equals 1, so if you're larger than square root log n, so if you're larger than log n, you are certainly larger than square root log n. Right? Here I'm just saying that you are larger than log to the A of n for any A. It's more interesting when, when A is a billion, right? It's very large.
Why is that not exactly equal to 1?
Well,
Maybe you don't have the mass exactly.
yeah. It's for non-interesting reasons. Okay, so let's see what happens under the alternative. It's going to be quite simple. So under the alternative, so when do we make an error under the alternative? So what is the probability that we don't reject under the alternative? That's equal to the probability by definition that omega, so under H1, that omega of g is less than k. Okay. So that's certainly smaller than the probability that if I look exactly at the k contaminated guys, these guys do not form a clique. If those guys form a clique, then that's it, they are connected and I have a clique of size k. So it's certainly smaller than the probability that there exists I not equal to j, and they are both of these guys are in S, the contaminated set. So there exist two guys which are not connected. such that xi, the inner product between xi and xj, is negative. Okay. If for every I not equal to j in S, this inner product is positive, then I have a clique of size k. So now let's just do a union bound. So what is the size of S is k, so I have k choose 2 times the probability under H1 that this inner product is negative. So what is this inner product? It's, let's rescale it by 1 over d, it doesn't change anything for whether or not it's positive. 1 over d, the sum for t equals 1 to n, xit, xjt is negative. So, sorry, sum up to n, up to d. Sum up to d. Up to d, yes. Yes, it's up to d, the dimension. Very good. So now what is the expectation of this? By definition, the expectation of this is rho. Right? So I sum things which have expectation rho, and I'm asking what is the probability that it's more than 0. So it means that it deviates by rho from its true mean. Okay. I'm summing d of them. Should be, if everything goes according to the plan, something like exponential minus a constant, d times rho squared. Right, the deviation squared times the number of samples. It's not completely trivial, right? These things are not sub-Gaussian, they are basically chi-squared, etc. But this is true. Okay, so what you do is you just compute the moment generating function of these guys. It's easy, right? It's just Gaussian random variables which are correlated. You apply Chernoff bound, and you get this with the constant being 1 over 10. So
the assumption under H1 is across the t's, they're independent.
Yes, I didn't say that, but that's very important. Yeah, so if you look at a slice for a given vertex I, yeah, it's an N0 identity. Yeah, it's crucial here. Because the elements in the sum are independent by coefficient. So now, what this means, so we want to, again, we have something trivial under the null, so we want something non-trivial under the alternative. So this is non-trivial if basically k squared times this is smaller than, let's say, 1/4. So if k choose 2, so k squared exponential minus this constant 0 squared is smaller than 1/4, then the risk, so the probability under H0 that we reject plus the probability under H1 that we don't reject, that's going to be smaller than 3/4. Okay, that's the result of our analysis. So another way to put this is that, so we have k squared, so it's something like, this is certainly implied by k squared, or let's say k is smaller than exponential some constant 0 squared. So if k is smaller than this, then we have a non-trivial upper bound. And you remember that k is the median of omega gen d. So what I'm going to be able to conclude, you will see, but I will say that this is not possible, so I will get a now we are almost at the end of the proof. So let's keep the statement. So the third step is actually the most difficult one. It's the only one which I'm not going to do in details, but it goes as follows. So what we can prove is that for any test, so this is called the risk. Right? This is called the risk of a statistical test, the probability under the null of making a mistake plus the probability of under the alternative of making a mistake. So for any test, the risk
would be this time to happen.
Right, so I don't want to rescale it, so I'm redefining risk as not with the one half.
So the statement is that risk in its classical definition would be lesser equal to 1/4.
Yes. Yeah, absolutely. Yeah, I understand why
Or
it
sorry,
would be.
not 1/4.
Yeah.
Less than
Less than 3/8. So, yeah. Something non-trivial. Yeah. So the traditional risk, you would get something non-trivial if you are strictly smaller than 1.5. And since I'm not rescaling, you get something non-trivial if you are smaller than 1. So for any test, the risk is larger than 3/4 if, so let's see if I can remember this, that's if rho, so rho is a correlation. Basically, if rho, right, if rho is 0, then this is impossible, right? The two distributions are indistinguishable. So how big can be rho so that it's still indistinguishable? Well, if rho is smaller than log n divided by k squared over d. Okay. So this is what is called a statistical lower bound. So if the correlation is smaller than this quantity, then you cannot test. The risk is larger than this. So I don't know how familiar you are with this type of argument. I mean, if you're not familiar with it, it seems completely magical. Like how would you prove this? It's actually really not difficult because if you look at the infimum over all tests of the risk of a given test, right? We want to, so over all measurable tests, you want to lower bound this quantity, right? So how do you get a handle on this inf over all tests? Well, that's equal, and that's called the Niemann-Pearson lemma. Niemann-Pearson. That's equal to basically 1 minus 1/2 times the expectation under the null of L of x minus 1, where L of x is a likelihood ratio between the null and the alternative. So L of x is just a Radon-Nikodym derivative of the probability distribution under the alternative with respect to the probability distribution under the null of your observation at x. Okay, so that's an equality. Right? So I moved from something which looks completely intractable to something that looks sort of doable. Right? I just have to look at the densities, and I perfectly know what are the densities, right? I have these two big matrices, I know exactly what are the densities, I can write down the formula with very few characters that give me this. Okay. Now, it's still not so easy because you have this absolute value of L of x minus 1. So what you do, is that usually you use Cauchy-Schwarz or Jensen. So the expectation, so now what do you want? You want to lower bound this, so you want to upper bound this guy. Right? So the expectation under the null of L of x minus 1, let's say by Jensen, that's certainly smaller than the expectation under the null of this guy squared. But now the nice thing is that look at what is the expectation under the null of the likelihood ratio. Well, by definition, it's 1, right? Because I get the dph0 that cancels out. I integrate dph1 x with respect to a common measure, and I get 1. So this is 1. So what is this? That's just the variance. Okay, so that's square root of the variance of the likelihood ratio. Okay, and now I'm happy because I have something that sort of looks simple and an operation that is sort of usual, the variance. And now I can start to do algebraic manipulations and upper bound this thing. The issue, why is this lower bound not totally trivial? So issue, in our model, so with the two distributions that I just erased, the variance is infinite. Okay, so that's sort of an issue. I lower bound this by minus infinity. Because it's not very good. So what you do, the trick, let me just give you the trick. is what you do is that you see these contaminated guys, I can write them as, so these xi's, they're equal to square root of 1 minus rho some yits plus square root of rho vt, where vt is a common signal across all the i's. Okay, that's the correlation. The correlation comes from a common signal vt, and the yits are the independent component. And now the key trick is that you condition on vt. And if you do that, then suddenly, for some reason that escapes me, this becomes finite. So if you condition on the vt's, the likelihood ratio becomes finite. And suddenly you can condition, right? It's like saying, okay, I'm telling you what is a common signal. Can you test now? If you can test when I'm giving you the common signal, it's suddenly easier. So the lower bound should be smaller. Okay, so you do that, and then we get this lower bound by finishing the computation. So now, let's see how we get finally this statement from step 3 and step 2, and that will be the end. So now what you do is the following system. Okay, so we know that if rho is that small, nobody can test. You cannot have a risk which is smaller than 3/4. So let's take rho. Rho is a free parameter in our problem. So let's take it to be, so k, remember, it's the median. We can certainly assume that k is much smaller than square root n. Right? We are trying to prove that it's super polylogarithmic. If it's already larger than square root n, okay, very well, this is true. If it's not, then this is just of order log n. So let's take rho to be of order log n over d. Okay. Then, what does step 2? Step 2 tells us that if k is smaller than exponential constant d rho squared, so what is rho squared? It's log squared n over d squared. So step 2 gives us that if k is smaller than exponential constant times log squared n over d, then we have a risk of this test based on omega, which have a risk which is smaller than 3/4. Okay, that's just this step. This with rho being log n over d. But now, by step 3, for this value of rho, it's not possible. Okay, it's impossible. Any test has a risk which is larger than 3/4. So this means that this cannot be true. Okay, so this implies that k must be larger than exponential constant log squared n over d. And k is the median of the clique number, which is exactly this statement. Okay, probability 1/2, you get k. So this is a little bit magical, but maybe, the open question at this point is, can we use this technique to prove anything else which is non-trivial and interesting? I don't know. Okay, for the moment, we applied it to this problem. One obvious next step would be to look at maybe the independent sets in a random geometry graph, but then you need to understand what is a good statistical hypothesis testing problem that corresponds to this graph parameter. Okay. And I don't know exactly how to do it. And I will stop here. Thanks.
There was nothing special about the median here.
Yeah, absolutely, yes. It's just to have a simple statement.
I have a feeling that when you are upper bounding the expectation on the H naught, Lx minus 1, it's essentially the total variation distance between.
Absolutely.
Right, and if you upper bound using Pinskers, that's the entropy, I have a feeling that you don't need to do the true.
So it's going to be less tight, right? If you start using Pinsker, then right, this is here. this is an equality, right?
Right.
And what you want to do is to lower bound it using Pinsker, square root of the group.
At least it's not going to be infinite.
No, it's not going to be infinite. That's certainly true. But I feel like it's not going to be tight. You see, maybe it is. I don't know. It would be very interesting to show that.
Actually, how do you see it's not going to be infinite?
Because they are not. I mean, they don't have any singularities, the two distributions. Right? You have two distributions on matrices, and they are absolutely continuous with respect to each other.
Right, but still conceivably the expected one.
Yeah. But I don't have any formal argument. Do you? I think it's true, but
Yeah, I think the intuition is that it's roughly the L2 distance. Right.
Oh, right.
Because the log of Gaussian, then
yes,
L2
okay.
distance. Then
Yes,
that's
absolutely.
phi is ND and everything is.
yeah, I think it's true. But I really doubt that it's going to be tight. I think you lose a lot by doing Pinsker and this set. But yes.
So, so that the median is not important, it's just probability of 1/2 in here.
Yeah.
But the probability of 1/2 and the probability of thin air is doing super with the thermal.
It certainly makes everything looks much nicer. If you start to make P not 1/2, then everything that was 0 becomes non-zero, and all the normalization becomes tricky. But you see, it feels like there's nothing really special about P equals 1/2. But there should be, just by continuity, should be that this statement is robust to small modification of P.
Yes, but what if P is getting smaller with n?
Oh yeah. Then okay. So then you get. I mean, you have many new questions, right? If you make P varies with n, if you make P, I don't know, 1/n or constant over n, critical regimes for the Erdős-Rényi, I have no idea what happens. But then the picture also becomes more complicated, right? You have D and P, and which varies at different rates with n, but many things are possible.
Okay, but you didn't explicitly do anything for P which is not 1.
No. I mean, the upper bound in the other paper by De Broglie et al., they do P fixed but not equal to 1/2, and they have explicit kind of ugly calculations because you have these TPDs which are highly non-trivial, etc. But everything simplifies this for P equals 1/2. That's why it's nicer. But I think one thing which is interesting is really looking at sparse regimes, right? When P becomes small as n goes to infinity. Then they don't have anything.
Could you check whether this sort of phase transition is evident in any real networks?
So I just checked this
Which
morning.
this model actually does sound kind of natural.
Right. So you mean, did I check in real networks?
Right, like in real.
Oh no. But I think it would be very interesting to do. Yeah. You can check experimentally. So I didn't do it either, and in the paper by De Broglie et al., they have some experiments, but it's not in the interesting regime, so it doesn't show any of these phase solutions. Yes.
So this question is slightly unrelated. So for the random geometric graph, what does the degree distribution look like? Does it have some sort of a head tail power law thing?
No. So no. So then, I mean, random geometric graphs are nice because it's sort of the simplest model where you have dependencies between the edges, but it's still far from a realistic model. So you have other things, right? Like I think you are thinking of preferential attachments and things like that, right? Where you have the zip degree distribution, but then it gets even more complicated, right? So here we are sort of in between something which is potentially really realistic and something which we can still analyze.
One second. So you mentioned the experiments, they're actually computing the peak number of the graph.
Yes, but of course it's for very small n. Of course. I mean, that's one thing, right? Is that if you want to do experiment, you are going to run into algorithmic issues.